Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to compute the volume of solids with known cross sections. Okay. Before we get started with an example, we're going to go over the strategy that we are going to be using to compute the volume of the solid with a known cross section. So first thing you want to do is you want to, of course, sketch the two curves um, and then label the bounded region R. That region is going to be, it could be the base of the solid or it could be a diagonal, depending on the problem. Step 2, you're going to orient the cross-sectional length. You determine the orientation of the side length of the cross-section on the region. In most cases, the problem tells you exactly how the cross-sectional length is going to be. Okay, it's either going to be perpendicular to the x-axis or perpendicular to the y-axis. Number 3, you're going to label your functions and limits of integration using the variable of the axis the length is oriented towards. So if the length is pointing towards the y-axis, then all the variables are going to be y. And if it's oriented perpendicular to the x-axis, then all the variables will be x, as will be illustrated in the problem we are doing today. Step 4, you're going to set up your integral using one of these two formulas. So if you have a vertical orientation, perpendicular to the x-axis, then everything will be x's. And then if it's a horizontal orientation perpendicular to the y-axis, then everything will be y's, as you can see here. Okay? And then step number 5, you're going to substitute and evaluate. What you're going to do is you're going to go back to this formula. You're going to sketch the cross-sectional shape. It could be a triangle, a semicircle, a square, whatever it is, you want to draw it, and then write the area of that region in terms of the cross-sectional length. Then after writing that area, you're going to then express the cross-sectional length as a difference of two functions. All right, and then when you accomplish that, you substitute that expression for the area in terms of the difference of two functions back into one of these formulas, and then you evaluate your integral for the volume. Okay, so we're going to be applying this procedure in solving the following problem. All right, so this problem is question 2B of the 2014 AP Calculus free response question. So it says, let R be the region enclosed by the graph of f of x equals x to the fourth minus 2.3x to the third plus 4, and the horizontal line y equals 4, as shown in the figure on the side here. Region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of the solid. Okay? All right, so this is the base of a solid. We have cross-sectional regions that are isosceles right triangles where one of the legs is sitting on this region right here, perpendicular to the x-axis. So what we're going to do is we're going to go ahead and sketch the situation. We have the steps on the side here we're going to be referring to. Let's go ahead and sketch the situation. Now, since this region is now a base, what I'll do is I'll tilt my y-axis at an angle, just lay it flat, lay my coordinate system flat so it's consistent with what the problem is, so I can generate a solid that looks like what I desire. Okay, so there goes my y-axis and my x-axis. Now let me draw this function right here. Let's draw that line. So there goes the line on top, and then we have the function, this function right here. I'll just sketch it. I'll make it green, something like this. And it goes down like that, and then like that. Okay. All right, so this is our region R. Is now laying flat on the side. That's R. This is my y-axis, and that's my x-axis. So what we have is a isosceles right triangles perpendicular to the x-axis. So let's just let's sketch one of the right triangles. Okay, so we want to determine the orientation. So since it's perpendicular to the x-axis, it's going to go look something like this. All right, and then that is a leg of the isosceles right triangle. So that's one leg. We're going to have another leg going upwards, perpendicular in that direction. And then we have the hypotenuse like that. Okay, so that is our one of the multiple, infinitely many isosceles right triangles we have in this region. Okay, I'm going to color it blue. So since it's an isosceles right triangle, this side is congruent to that side. Okay, so we have a sketch, and we see the orientation of our the length that is the cross section. So we can now advance to part B. So we have to label our function and limits of integration using the variable of the axis the length is oriented towards. So since it's pointing towards the x-axis, our triangles are going to be going from left to right. Okay, so everything is going to be in terms of the axis is pointing towards, which is x. Okay, so let's go ahead and label. If you're going in this direction, this is the bottom, that's the top. So this function right here is going to be, let's put it over here, f top of x is going to be 4. Okay, that's the top function. Now the bottom function is going to be the green one. So let's label it right here. So f bottom of x, again, is going to be the function that we have up here, which is x to the 4th minus 2.3 x to the 3rd plus 4. Okay, plus 4. All right, so that's the top function. The black one, that's the bottom function. Remember, this is the region that we're looking at right here. Okay, this is the top, and this is the bottom. Okay, now we have the top and bottom functions. Now we need the points of intersection. So I'm not going to go over that right now. Let's assume that you know how to use your calculator to find the points of intersection. Now, the point of intersection here is going to be 0, 4. But what do we need? We need the x's. We're going in the x direction. So our lower limit of integration will be a equals x equals a, which is equal to 0. Okay, that will be our lower limit of integration. So we're going to have x from the left, okay, which is equal to our a, and that's going to be 0. Now over here, the point of intersection here, if you use your calculator to calculate it, this will be 2.3, 4. Do we need the x-axis or the x-coordinate or the y-coordinate? We need the x-coordinate. That will be our upper bound. So taking that out, we're going to have the x on the right is going to be b, which is equal to 2.3. Okay, so that's what we're going to do. So we have the functions, we have our lower limit of integration and our upper limit of integration, all in terms of x. Okay, now we have everything labeled. Next step is we're going to set up our integral. Okay, so let's go ahead and set it up. This is going to be a vertical orientation. So the volume V is going to be the integral from x to the left, from the left to x on the right of the area a of x dx. Okay, so this is the expression for the volume of the solid. Okay, so we already know what the limits of integration are. We're going from 0 to 2.3. We need to figure out the a of x part. Okay, so now we're going to advance to part 5. We're going to sketch the cross-sectional shape. So So what's the shape of our cross-sectional region? It's an isosceles right triangle. Okay, so let's go ahead and sketch that. Okay, so there goes our isosceles right triangle. Now we're going to try and figure out the area of this shape in terms of the cross-sectional length. Okay, so what's the cross-sectional length? We should have labeled that. This region right here, let's call it L. Let's call that L. So that's the side length that is the cross-sectional length. Okay, so if that is L, that means this is the 90-degree portion right here. This is the bottom, so that's L. Okay, so what's the area of this isosceles right triangle in terms of L? You have to be really careful. It has to be in terms of the length, whose length is the cross section. Okay. All right. So this is L. Now, what's the area of this isosceles right triangle? So this is an isosceles triangle. This is L. This is L also. And we know that the area of a triangle is what? 1/2 base times height. In this triangle, this is the base and this is the height. So our area, the area of this triangle, is going to be 1/2 L times L, which is 1/2 L squared. Okay? So this is the first part. You express the area in terms of the cross-sectional length. Now we have to express the area as, we're going to express the length as the difference of functions. Okay, so what is this? How long is this L right here? L is basically, this segment right here is basically the top minus the bottom, the black portion minus the bottom portion. That would give us the length of this region right here. Okay, so let me show you. This region right here is simply the top minus the bottom. Okay, so let's go ahead and apply that here. L is equal to f top of x minus f bottom of x. Okay, so that's the principle we're going to be applying here. F top is 4. F bottom is that function. The blue function right here, that's the bottom. X to the 4th minus 2.3 x to the 3rd plus 4. Okay, so that's what the length is in terms of expressed as the difference of two functions. Now, what we're going to do is rewrite the area using that. So the area in terms of x of the cross-sectional shape is 4 minus x to the 4th minus, actually minus times minus makes that a plus, plus 2.3 x to the 3rd minus 4. Okay, so that's 1/2 of that, 1/2 of that length quantity square. This entire piece right here is L. 1/2 L squared is the area. We can simplify it a little bit more. We have 1/2. 4 times minus 4 is 0. 1/2 times x to the 4th plus 2.3 x to the 3rd quantity square. So that's the area. Now that we know what a of x is, guess what? We're going to plug that right back into this original formula that we have here, also implementing our limits of integration. So the volume is going to be the integral from 0, that was a, to b, which is 2.3 of a of x, which is 1/2, times, should be a minus here, negative x to the 4th plus 2.3 x to the 3rd power raised to the 2nd power dx. Okay, so we're simply plugging this expression into our calculator to see the value of our volume. Okay, so if you plug it into your calculator, as you can see here, I'm using the TI 89 titanium. Plug it into your calculator, you get 3.574. Okay, so the final answer is 3.574. Okay, so just a visualization to help you see what the result looks like. So if we take that region that we had earlier, and when we rotate it, lay it flat, and then just take a look at the orientation of the rectangle. So those are the isosceles right triangles that we're talking about. And then we take the infinite sum of all the areas. That is the resultant solid that we're going to have. Okay, so that's what the solid looks like. And we want to compute the volume. That is the setup. And then our volume will look just like that. All right, so that is that. Thanks so much for taking the time to watch this presentation. I really appreciate it. Um, Just feel free to subscribe to our channel for updates to other cool tutorials such as this. If you have any questions, comments, feel free to include it in the comment section below, and we'll be glad to address it as soon as we can. More clips can be found on mathgotserved.com. Be sure to visit it. Thanks again for watching, and have a wonderful day.